Now we are ready to discuss about the single crystalline solid. In the last slides we have discussed about what is a single crystalline solid, so what is a polycrystalline solid, how the crystal lattice arranged in the single crystalline solid, how it is arranged in the polycrystalline solid. With the picture we have studied. Now we want to study about some important characteristics of the single crystalline solid. That is the thing we are going to study in this topic, the single crystalline solids. Crystalline solid, there is a single crystal have an periodic array of atom in its whole volume. Even if you are moving in along the x direction, it will align in the periodic manner. If you are moving in the y direction, it will align in the periodic manner. Suppose if you are moving z direction, it will align in the periodic manner. So if you are moving in any direction, the atomic arrangement are in somehow periodic. What do you mean by the periodic means? Suppose if you are having the atom in the x direction, if you are just take that axis, three axes, this is a z, this is a x, this is a y. So here you can call it as x, this is y, this is z. If there isn't one atom at the origin, if you are taking that origin, suppose if another atom is placed at a distance a, then the third atom also it is placed at a distance a. The distance between the nearest atom is a. The fourth atom also placed at a distance a from the third atom. So similarly, the atoms are arranged in the z direction also. Suppose this distance also a, this is also a, this is also a. This is the some periodic manner, so it will be arranged like that. If you look at the y direction, the distance also it's similar to what we have seen in the x as well as in the y. The uh, periodicity means the distance between the any two atom, it will be same manner. Even we can call this as a cubical lattice because it's looking like a smallest volume in this space. It is a cube. Anyway, with that we are going to see this is a periodic array of atom. Even if you are measuring the electronic density at the x equal to 0, y equal to 0, z equal to 0, the electronic density at x equal to a, y equal to a, z equal to a, it will be same. Even if you are measuring at any other distance, if x equal to 2a, y equal to 5a, z equal to 10a, that vector, suppose if that vector is represented like that, then the electron density again will be same. That is the periodic array of an atom. That means the electronic distribution, the atomic arrangement will be the periodic. In the crystalline solid, we can call that as a single crystalline solid. The next point, here it is shown by the diagram. Here it's shown, it's like a 2D lattice. This is this axis you can call it's a you may take it's a y axis. You may take this axis as x axis because this lattice represented by a two-dimensional vector. We can call it a single crystalline solid in two dimension. What are the other characteristics of the single crystalline solid? If you look at that one, so it possesses the translational symmetry as well as the rotational symmetry. What do you mean by the translation symmetry? Means suppose if you are just to think at a equal to at a distance a equal to one atom, then 2a also having one atom, 3a also having one atom, that is kind of translation symmetry. So at a distance it is having only one identical atom. At 2a distance the same identical atom will be there. 3a also the same identical atom will be there. Even if you take that r equal to, that's in general in the 2D vector, some 2i vector plus 3j vector. if you look at this distance, that means in the x-axis 2a distance, maybe you can call it a 2a. I have taken as a unit vector, but you can call it in terms of the atomic distance, interatomic distance, you can represent this vector. So this vector represents, suppose if we are taking, this is the origin, 2a x direction, 2a here, 3a y direction, 1 2 3. So it will represent, but here it's not exactly the square lattice, because if you see the square lattice, it will tells us x equal to 2 in the x direction, 2, y equal to 3, 1 2 3. This is a 3 atomic distance. If you look at that, the atom is located at this distance. So this atom represented, suppose here this axis is x axis, this axis is y axis. So this atom, in this location of this atom, is represented by the vector r, that is given by 2a, because at x distance, if you look at that atomic distance, here I am missing one atom, 1 2, the lattice parameter is 2, y axis 1 2 3. So this is in general the r vector represented by r equal to 2a plus 3a. This is a translational vector. That means if you look at that at this distance, x equal to 2e, y equal to 3e, that represented by the r vector, the diagonal vector. At that point also, it is having the identical atom. That is the meaning of the translation symmetry in the single crystalline solid. Look at this diagram, it will explain clearly. Here, because we have all the atoms are identical atoms, we are just assuming we are taking single crystalline solid. So all the atoms are in the single crystalline solid identical. That means at the position r vector, the atomic arrangement is identical. That is the meaning of translational symmetry. Even if you are moving, if you look at from the r, if you look at your surrounding, it will be same. That is the single crystalline. What is the rotational symmetry means? Suppose if I am rotating this crystal system by 180 degree about this axis, again it will be remaining same structure. But if you are rotating 90 degree, you can't see the atom, it's a 2D lattice. First initially it will be like that. If you are rotating 90 degree, it will be line. If you are looking like this, it will be line. Suppose if you are rotating 180 degree, then only you can see this atomic arrangement. That means it will be remaining same configuration. That is no rotation. After 180 degree rotation, it will be remaining same along the y direction. Even you can rotate about the x axis also 180 degree. After rotation of 180 degree, again the atomic arrangement will be same. This is a kind of symmetry we can call rotational symmetry. So the single crystalline solid possesses the translational symmetry and rotational symmetry, or okay, and you have to use here, and this both symmetry can occur in single crystalline solid. The next property, if you look at, it has long range length scale. Each atom is related to every other equivalent atom. If you look at the single crystalline solid in 2D lattice, it have, even you can extend beyond this given diagram also. It has a long range length scale. Whatever we are saying, like a few number of atom. If you are counting this number of atom, 1, 2, 3, 4, 5, 6. So 6 atom in the top row. The bottom row it will be like a 7 atom, but 7 6 atom, it will be not the case for the actual crystal. Billions of atom, millions of atom. That's why we are saying it is long range length scale in the microscopic world. So each atom is related to every other equivalent atom. Even if you are taking each atom, so you can see some configuration between these three atom. Even if you are look at the number of nearest neighbor, it will be same. Even if you are taking this atom, the number of nearest neighbor, it will be equal. That's why each and every atom is equal to other atom by somehow, by its number of nearest neighbor, or by number of the electronic number of electronic clouds surrounding in it, or that some other property, it is related to say equivalent to other atoms. So that is the third point. If you look at that fourth point, no grain boundaries. I told what is the grain boundaries. Grain boundaries means it's a boundary between the one type of crystal to other type of crystal. So suppose if you have the some square lattice here, if you have the some hexagonal lattice here, there is in between gap, that is a grain boundaries. So but if you look at the single crystalline solid, there is no boundary. We saw the polycrystalline solid, exactly there is a boundary, that is a grain boundary. But here it is not the case. There is no grain boundary in single crystalline solid. If you look at that, no defects in the single crystal. That is surprising because single crystal is most perfect crystal. Look at the crystal. There is no gap. There is no crack. This is an ideal crystal. This is the one we have drawn. We have take the picture from the Google, but actually if you are manufacturing single crystalline solid, it is difficult. Then only you can feel how much it is difficult to make the single crystalline solid. If you are asking the manufacturing, then they will explain what are the difficulty they will experience while making the single crystalline solid. But ideal single crystalline solid, there is no defects that we can conclude. So there is for single crystalline solid, mechanical, optical, electrical property it is having. It is an anisotropy property because electrical property I already told, in the x direction it is different from the y direction. It is different along the z direction. Even if you are see the diagonal, if you are sending the some electronic current along the body diagonal in the cubical lattice, then that will be different from the other face diagonal. So that's why we are calling the single crystalline solid is perfect anisotropic crystals. If you look crystalline solid, how we can study about the single crystalline solid? That is the first question we can ask. But that is a experimental method for studying about the single crystalline solid. That actually we are not going to discuss in this unit. Maybe at the end of the unit, they will discuss about the experimental method. Even we are not going to discuss about that X-ray diffraction. We are not going to discuss about the electron beam as well as the neutron beam diffractions. Here we are studying only the basic terms involved in the single crystalline solid. So what are the basic terms we needed to understand the single crystalline solid? This question we can ask because the basic terms are important to understand any topic. Here what we have chosen here means in the unit 5, the crystalline solid. Now we are standing at single crystalline solid. So we need to understand to form or to for the its formation some basic term. What are the terms that we are going to discuss in this part? First term involved in the single crystalline solid, that is space lattice. Space means actual we are living in space, that we can call that is a space. That space is occupied by the some point that anyway we are going to discuss. The next term we have to understand in the single crystalline solid, that is the basis. Lattice is a some imaginary concept, that is point. Basis also we are going to see. The last term that is involved in the single crystalline solid, that is a unit cell. This not only for the single crystalline solid, the space lattice basis unit cell. It is a general concept for any crystal lattice, even for the polycrystalline solid also. So if you know these three things, then we are ready to do the complete analysis of the crystal lattice. We can actually, this is a building blocks of the crystal lattice in the theoretical, on the theoretical basis. So we can call this is a theoretical foundation of the single crystalline solid. We are going to discuss now. The first term is a space lattice. So what is a space lattice? We can ask that question. Yeah, lattice is a regular and periodic arrangement of the point in the three dimension. You can put the point. That means, sir, shall we put the atoms in the point? No. Lattice is a just imaginary concept. You can just, if you are making the point like this is a lattice. These are the lattice or lattice points you can ask. Not only the one direction, you can just put the point in the y as well as in the z direction. The other direction also just you can extend. So this is a periodic arrangement. That is the word you got to look at. The regular periodic arrangement of the point. We can call it is lattice. How we can define it properly? So the definition is, it is defined as an infinite array of points in three dimensions in which every point has surrounding identical to that of every other point in that array. This space lattice is otherwise called the crystal lattice. So in space, we are just making the points in the periodic manner. Those points are called the lattice because it is in the space. We can call it a space lattice. So now this is an important definition we want to know. I want to just explain little more clear using the diagram. Look at this diagram. Here the points are arranged in the beautiful manner. There is a periodicity. If you look at that x direction, see the point P, there is one atom. At a distance, there is one more atom. There is one more atom after from the point P at 2a, from the point P at the 3a up to Q. It's arranged in the periodic manner. At equal interval of a, there is an atom. Not only along the PQ line, even above the PQ, below the PQ, there is a row of atom is arranged. If you look at the y direction, suppose if you look at other direction, because it's a 2D lattice, the one more direction is y direction. There is an also periodicity. See here, the if you are taking the atomic distance, the distance between the, sorry, we should not use the word the distance of the atomics. Here the points, the distance between the 2 points, if it is b, then the third point as well as the second one, that is also b. Here also it is b. The one more atom at b from the previous atom. So there is a periodicity in the y direction. There is a periodicity in the x direction. We can relate one point to every other point. Suppose if I am taking the point A here, so I want to draw it here alone. This is a point A we mentioned in the diagram. Before making that point, I want to make the conclusion. If the x the lattice parameter. Lattice parameter means here A. Here lattice means it's a point. The distance between the 2 points is A. That is why we can call A is a lattice parameter that will define the distance between any 2 points. So if A equal to B, the distance between the any 2 point in the x direction, that will be equal to the distance between any 2 point in the y direction. We can call in general this two distance A. Now we are doing some calculation. How we can measure the distance between any other point? It's just a simple Pythagorean theorem. Suppose if I want to measure the here nearest point, suppose if you diagonally I measure the point C, this you can call C. What we can do, these are the rectangle triangle. This distance also A. The now we are taking the y distance also B, that will be also equal to A. What is the distance between A and C if you are just measuring? Just a simple Pythagorean theorem, because the two adjacent two side making the angle between the two parameter, the x as well as y, it's 90 degree. If you look at this, it's 90 degree. So just we are measuring the diagonal. Using the hypotenuse theorem, we can tell the AC is equal to adjacent square, then the other two, sum of the other two sides square, a square plus b square, that is equal to the diagonal square. Then if you are measuring the AC distance, that will give, because B equal to A, so A square plus A square 2A square, that will be equal to AC square. If you want to measure the AC equal to, take the square root on both sides, it will give square root of 2 times A square, square root will get cancelled, it's a square root of 2A. That is given in the, here look at this diagram, it is given this distance between the A and C. Likewise, you can find the distance between the A and D also. How you can measure? Again, we are going to use a Pythagorean theorem. Here A lattice parameter, this distance, the vertical distance is 2A, because there are two atoms. So this distance is 2A, then the bottom is distance is A. If you are asking the diagonal distance, A and D, but in these 2 point A and D, definitely this distance, it will give square root of 5A. Again, just to use the Pythagorean theorem, you will get that the distance between A and D. So somehow each point is related to other point by somehow the distance here. Now we are just measuring the distance. So you can measure any other point distance like that using the simple Pythagorean theorem. So this is a space lattice concept. Only just we have discussed about the point without an atom. Now, if you are placing the atom in each and every point in the space lattice, what is that thing? If you can ask one question, just to put a one by one atom in the point, what would happen? If you are placing the atom each and every lattice point in the space, that points now it will call as a basis. Basis is with the atoms, that is the meaning, or with the molecule that point is represented, that we can call as a basis. Here actually the dot already we have took the picture. Suppose if you are placing the dot using that atom, suppose the blue color represents it's like a atom, maybe it's single atom, you can take it's copper or iron, but that crystal lattice in 2D I am just making the sheet, I am placing each and every point by an iron atom or copper atom or gold atom. So now the blue colors points we can call that is a basis. So these are the, maybe you can just fill up all other points. Now you can relate that basis also using the same relation distance between the any two bases. Now we are really speaking about the atom basis means. So how we can define the basis? So a crystal lattice is formed if each lattice point is filled by an identical atoms or molecules in a given periodic array. This unit assembly is called basis. When the base is repeated with the correct periodicity in all direction, it gives the actual crystal structure. This is the actual definition for the basis. Now you understand the conceptually, you can understand the theoretical way, how you can define the basis. So, what is the difference between the basis as well as the lattice? You can ask that final question here, because this is the second term we are seeing in the crystal lattice. So this important definition, the crystal structure is a realistic structure, but the lattice points are imaginary. Which one is a real means the basis. Without atom, if you are making only the point to explain everything, just that is a simply lattice. With the point, if you are explaining the everything with the points means with the atoms, then that is called the basis. So you can give the important conclusion, the lattice is an imaginary, the basis is real. The real plus imaginary, what is real plus imaginary? Uh, is that real? Of course here it is real, but mathematically we can't say, conceptually we can say it is a real. How? Here we know the basis, that is an actual atom we are placing in that imaginary point. Then the lattice an imaginary point. If you are combining these together, the addition of these two, it will give the crystal structure. This is an important concept we want to understand before starting the crystalline solid. So this is a complete picture it will give about the crystalline solid. Even if you are just writing using the pen and paper or blackboard on chalk or whatever, if you are using this kind of online material, if you are making that point, that is an imaginary. If you are each point, if we are represented using the atoms or ions or molecules, that is we can call basis. This together it will give the complete picture of about the crystalline structures. Now we are ready to discuss the last term in the crystal lattice, that is we can call that unit cell. How you can define the unit cell? Unit cell means the smallest volume can be repeated in all direction. That is the smallest volume you can call the unit cell in the crystal. So we have to define properly what is a unit cell. Yeah, unit cell is defined as a fundamental building block of a crystal structure which can generate the complete crystal by repeating its own dimension in various directions. So this we can call the unit cell. Suppose if you are taking that unit cell is a cubical volume, you have to define the parameter first in this unit cell. I am taking the x parameter is a, y direction also a, the z direction also a. Then you can define the volume of the unit cell. It's a cube because it's a cubical structure. You can call this unit cell is a cubic unit cell, or you can call it a simple cubic unit cell. Anyway, that we are going to see in classification of the crystal structure. Right now, this is a unit cell. What we are going to do means we are going to repeat this structure in the x direction, y direction, z direction to form a complete crystal structure. Because if you look at the definition, the fundamental building block of a crystal structure which can generate the crystal structure, we got to repeat its own dimension in various direction. Here in various direction means in the three-dimensional space we get three direction only. So we got to repeat this unit cell in three direction. Suppose if I am repeating this unit cell, first place it at origin. What I am going to do, I am going to take the same unit cell, I am going to place it one by one in the x direction. See here, I am repeating the cubic cell in the x direction. Now I got to go repeat this same unit cell in the y direction also. 1, 2, 3. Like that I can repeat. Not only 1 and 2, there is a third axis because we have to repeat in the other dimension, the third direction also. So in the z direction also, you can place the same unit cell. If you are placing, it will generate the complete crystal structure. If you want to exactly, if you want to generate, you got to repeat row by row in the x direction. See here, it is actually looking like one wall because it's looking like a brick, so it will form one wall kind of thing. So crystal structure also it's looking like that. Suppose not only if you are repeating that wall in the other direction, that it will form a complete crystal structure. See here, in this direction also you can repeat. So if you are repeating, then if you fill up all the box, that means it will form a complete crystal structure. So here we are just taking the cubic unit cell, the fundamental volume in the crystal lattice, we are repeating in all direction. Now I have shown here example. You can repeat in the x direction up to infinity, y direction also up to infinity, because inside the crystal there are billion power billions of atoms will be there. Here in the simple cubic only 8 corner having 8 atoms. Billions of atoms means you can think billion power billions of atoms means you can think this fundamental units of how many it will repeat, even more than billion power billion. So by that way, you can form the crystal structure. So in this topic, what we have studied means we saw the single crystalline. Mainly we have concentrated the three terms. One is the lattice, space lattice, that is the imaginary point. The second one is basis. If you are placing that in that imaginary point using that atom or molecule or some other particle, we can call that is a basis. The lattice, the basis, both will form the crystal lattice, the crystal structure. The fundamental volume or fundamental block in the crystal lattice, we can call as a unit cell, the third term. If you're repeating that unit cell in all direction, it will form a complete crystal structure. Now in this chapter, in this discussion, we have studied how we can form the complete crystal structure.